I'm going to give a pretty non-traditional presentation of the Fundamental Theorem of Calculus, and the real reason is I want to connect that to multivariable generalizations of the fundamental theorem. But we really are going to stick with the situation of BC calculus. So let's say we have single variable calculus situation. Here's something we could imagine. We've got a rod, some sort of like metal rod perhaps, and maybe here's position 0, here's position A, and here's position B. And so maybe here's one end of the rod, and here's the other end. And f of x is the temperature along the rod. And one reason I'm picking that is I want to actually not be very tempted to draw the graph of it. We'll draw the graph of it sometimes, but it's kind of nice to have something where we don't feel like we want to draw the graph too much. I'm not focusing on the area interpretation, for one thing. Okay, we could draw the graph, certainly, A to B, and maybe it's colder at A, well, colder on this side than here. It's hotter over here, so I'll put cold, hot. But I want to actually, as much as possible, stay in one dimension, because in the multivariable setting, we won't necessarily have extra dimensions to work with. Okay, and so I want to think about this version of the fundamental theorem. It's called FTC 2 in Stewart, for example. What does it mean? What does it calculate to take the integral from A to B of the derivative of that temperature function? And the claim is, fundamental theorem says, that's the total difference. The integral of a rate of change is the total change in the temperature. So why would that be true? Well, what I'm going to do is I'm going to take that f of b minus f of a, and I'm going to do something that's sort of the basic operation of calculus. I'm going to segment the rod up into a bunch of little segments. And so let's call this x sub 0 and x sub 1, x sub 2, x sub 3, up to x sub n. And then right before it would be x sub n minus 1. So A is x sub 0 and B is x sub n. It's a very standard technique. In here it would correspond to starting out like a rectangle method calculation for a Riemann sum. But I don't want to focus on that so much. I just want to look at f of b minus f of a, and I want to calculate it in a sort of gloriously stupid way. This is the overall change in the function. And I'm just going to break that down into, it's the change on this last interval, this last little subinterval, plus the temperature change in the interval right before that. That's from x sub n minus 2 to n minus 1, plus dot, 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 plus all these sums of the temperature changes, and plus f of x, say 2 minus f of x1, plus f of x1 minus f of x0. And I just want to observe how incredibly simplistic this is. All I'm doing is I'm writing out a bunch of differences, and each one of these internal differences cancels. Minus f of x1 plus f of x1, minus f of xn minus 1 plus f of xn minus 1. So there's two ways to convince yourself this is true. It's the overall change. That's equal to the sum of all the individual changes in the temperature. Or you can just look at the algebra and say, hey, this is what's called a telescoping sum. Everything cancels out except the first and the last. So the way I want to express that is that there's internal boundaries. That word boundary is going to be very important. The internal boundaries that we put in artificially, they cancel out. And so the contributions from those internal boundaries cancel. And the what's left, that just leaves the global boundary, the boundary of the whole entire region, and that's just A and B. So this is just, of course, f of A, and this is just f of B. just leaves the global boundary. Okay, so I want to say a little bit more about this internal boundaries canceling. Whenever you have a segment, then there's a couple of things that are going on. One is that we are purposely have a direction of integration here. We're really going from a to b, and that's important. Remember, the integral from b to a is minus the integral from a to b. So there's a direction here on the whole segment, and that gives a direction on all the little subsegments. That's how we know to take, for example, f of x1 minus f of x0 and not the other way around. And each of these segments, the big segment, for example, has boundary a and b. But it's going to turn out that it's very useful to count those with a sign, that if it's at the head of the arrow, we use a plus, and at the tail of the arrow, we use a minus. And we can also say the boundary of each little segment, like x1 to x2. The boundary of that is these 2 points, x2 and x1, but this one counted with a plus sign, this one counted with a minus sign. Well, what about this little subsegment in here? There, x2 and x3 are the boundary pieces, but this counted with a minus and this with a plus, because this is on the tail of the arrow. This is on the head of the arrow. So if we have that kind of formal accounting of how many different boundary pieces do we have, we see that x2 gets counted twice, once with a plus, once with a minus. And that's exactly what happens here when these guys cancel out pairwise. That's going to be important. Okay, so let's think about this in terms of a little bit more sophisticated presentation, and we're going to have sigmas coming in. So f of, let's just focus on one of those internal pieces. The main work, in a way, the main work is already done. This idea of taking the whole change and saying it's the sum of local changes. The rest of it is just kind of working out the details of, is there some other clever way to write those local changes? Okay, so the temperature change from xn minus 1 to xn, for example, that first one, that's this one, I guess. Okay. We're going to have, that's approximately equal to the rate of change at some point in that interval. So I'm going to use the Stewart's notation that, let's say x sub n star is some point in here. And we're just going to pick some random point in there. Okay, so this is where the derivative comes in. We just now need to know that a small change in the temperature from here to here is given by the rate of change of temperature by how far you went in x. That's just basically the meaning of the derivative. It's a rate of change. If you take this over here and divide it, it's saying that the rate of change at a point in here should be very close to the overall rate of change from the left-hand endpoint of this guy to the right-hand endpoint. And that approximation is going to get better. It's going to get better as these pieces get bigger. In other words, as n goes to infinity. Now, if you want to be really fancy about it, the mean value theorem actually guarantees that there's at least one special xn star we could pick to make this an equality. But that's not really that important. Okay. So, in other words, let me just rewrite that. It's f prime of xn star times delta x. So that says that each local change has to do with the derivative and also how big the local pieces are. Okay. So, let's see. I think I'm going to need to have all the space. Okay, so now the whole point of this, or a lot of the point of this, is we want the delta x to go to 0. We want not approximations but equalities, and we want to get integrals coming in here. Okay, so f prime of x, that's the limit, as we know, as delta x goes to 0 of exactly the kind of thing we were looking at. Let's keep focusing on one of those segments. Let's say the nth segment, doesn't really matter. Okay. The derivative is you take the difference in the temperatures divided by the difference in the x's, and you take the limit as delta x goes to 0. And so, let's put together so far we've got. We've got the overall change is approximately equal to the sum over all of those intervals of the local changes. Then the local changes Now here, I want this to be xk star, because now instead of focusing on just one segment, I need it to work for each of the segments, times the width of each segment. Okay. Now, as I take n goes to infinity, we know what this turns into. The sum of a bunch of numbers times delta x, that turns into the integral from a to b of f of x dx. And that is now f of b minus f of a. Okay, so that is the fundamental theorem showing up. Now, I want to present this in a slightly different way, because it's going to be really interesting to us in the multivariable case. I want to talk a little bit more about the delta x turning into dx thing. Okay, let's see if we can streamline this. We really would like to say something like this. The integral of f prime of x dx, f prime of x dx, if we can treat this really a little cavalierly, that's an infinitesimal change in x times the rate of change of f with x. Well, that's just an infinitesimal change in the function f, the temperature. And we'd like to say that if I add up an infinite number of infinitesimal changes, I get the whole change. That's the way they described it when they first started calculus, but it's pretty suspicious. Okay, it seems to be saying that f of b minus f of a is an infinite sum of zeros, because all these infinitesimal changes can't really, if I don't let x actually vary, I can't let, then f isn't going to change. Okay, that doesn't seem to make a lot of sense. Okay, so what we're really doing is we're taking f of b minus f of a. Let's go back to the very low-tech thing. It was f of xn minus f of xn minus 1 plus, let me put it down here, plus f of xn minus 1 minus f of xn minus 2 plus dot 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 plus all the way down to f of x1 minus f of x0. If I just tried to take n and it goes to infinity in this expression, that's not going to work very well, because these differences are going to get smaller and smaller. As I chop up my interval from a to b into tinier and tinier and tinier pieces, these guys are all going to go to 0, but the number of them is going to go to infinity. So that seems to be going towards this idea of, okay, the sum is getting out of control, too many things summing up, but then the things inside it are going to 0. The way to make that work is to start talking about rates of change. I'm going to look at the sum of the rate of change times the change in x, and then the rate of change over the next interval times delta x, and that all times delta x. And the advantage of that is I can just factor out that delta x. Now, what's going to happen? These quantities don't go to 0 anymore. These are rates of change. And in fact, when I take the limit as delta x goes to 0, this exactly just gives me the derivative right at the end of the interval. This gives me the derivative near the end of the interval. This gives me the derivative over at the start of the interval. And so it's really crucial to have this very simple step of, instead of talking about actual change, talking about the rate of change, or what we're going to refer to it pretty soon is the density of change. And so now, as delta x goes to 0, I have a sum of numbers that aren't getting weird. They're actually converging to some nice function, the derivative of f. And I get an infinite sum of nice numbers times delta x. That's exactly what turns into a derivative, or it turns into an integral. So this thing is something that makes sense as delta x goes to 0. That turns into the integral of the derivative times dx. The delta x turns into dx. These density of change numbers turn into the f prime, and the summation process turns into an integral. Okay, so let me summarize the point of view here we have on the fundamental theorem. The ingredients are, we have a boundary, well, we have a region. Let's see if that'll fit up. Let's see. We have a region, which is the interval. This guy, A to B. It has a boundary, and we seem to want to attach an orientation to everything so that the region is oriented in a certain way, the direction of integration, and we have plus and minus attached to the boundary pieces. Okay. Then we chop that up into small pieces with internal boundaries that cancel. Okay. And then on each piece, we look at the change, but we actually look at the density of change. Usually called the rate of change, but here I'm going to call it the density because in 2 dimensions, the rate isn't going to make much sense. Okay. And then what we say is that the overall change on the global boundary, that's f of b minus f of a, said in kind of words. That expression, we express it as the sum of all the local changes. That was that collapsing, telescoping sum. But then we re-express it as the sum of density of a product, density of change times the delta x. And then we take the limit. As delta x goes to 0, this turns into the integral of the derivative. Density of change turns into the derivative, the sum of and the delta x turns into the integral on the dx. And that's another way to think about the fundamental theorem of calculus. And all of these ideas, region, boundary, internal pieces, canceling, orientations, density of change, that's all going to come into all of the versions we'll do of the fundamental theorem.